Okay. Good afternoon. Does anyone hear us clearly?
Yes, yes, yes.
Okay,
They're
good,
saying
because I don't
yes.
see the chat. They just sent to you. Okay, good. So good afternoon, everyone, and welcome to today's webinar. For the new participant who missed to join the last week opinion session, my name is Sana Nuzri. I am the host and the organizer of the online webinar. So I am happy and thrilled to have you all here today to discuss the first webinar, which is about AI revolution, tracing the journey from foundation to future frontier. It's the webinar that is linked or related to the first online chapter, what is AI. So again, thank you so much for your participation. We appreciate your dedication for the online chapter and as well for the online webinar. We hope that you complete the first online chapter, what is AI, because it's very important to complete it, to be able to attend the online webinar, which we complement the content by the current information and fresh insight. So also we hope that we see your question in Reddit. You can post them before the webinar so that we can answer as much as possible before the webinar. So I would like to introduce our first speaker for this webinar, Dr. Joris Hulsten. He is a postdoc researcher at the Department of Computer Science at the University of Luxembourg. He has a background in information system and artificial intelligence. He has recently joined the Day4Age project, Digital History, in which many PhD candidates and supervisors collaborate on in the topic of digital history. So Holstein research topic is responsible AI, which is related to explainable AI, but also to more mundane aspect of governance and the control. So we are honored to have him today for this webinar to share their work, insights, and experience with us. During the presentation, if you have any question or comments, please, we encourage you to use the Q&A session, not the chat, but the Q&A session to post your question. We will be moderating them. I will try to ask some question in the chat if I can. Otherwise, I will be giving them after the speaker talk to answer them directly. So please don't hesitate to put your question in the Q&A session. If you have access, all of you, to the Q&A session, it's highly recommended to post your question in the Q&A session. Otherwise, for those who cannot post their question in the Q&A, they can use the chat to post as well their question. We will be looking to it to them as well. So our speaker will be presenting for approximately 45 minutes, followed by the Q&A session, 15 minutes. Also, we have 15 minutes additional to answer as much as we can the question. So we will follow up afterward if we cannot answer all the question in the Reddit. So please, for those who cannot get answer for their question, they can post them in the Reddit. Just look at the post or the blog related to the webinar. For example, we are at the webinar 1. You should write your question in the Reddit, which is related to the webinar 1 after this presentation, if we cannot answer them. So we will be recording the webinar every week. So for those who are unable to attend or want to rewatch the webinar later, so it's also possible. We will put the link in the post of the webinar every week in the Reddit. So I hope that all of you have access to it. So please, if you have issue to access to Reddit platform, just mention that in the chat. We will be trying to fix the issue with you. So without further ado, I would like to turn it over to our speaker to begin the presentation. Dr. Joris, the stage is yours.
Hello, and welcome to this lecture on AI. So yeah, you will have to get used to my voice a little bit. As Sana explained, I did a lot of research in AI. I started in 95, more or less. My PhD was in 2000 on natural language dialogue systems, and I've been following AI, in particular a subfield called multi-agent systems. So that's group of AI systems. And that's my expertise. And now in Luxembourg, I worked on explanation. But that topic is much better explained by my colleague Amro later on. Okay, so for today, yeah, we have to start at the beginning. Let's start at the beginning. What is AI? So the abbreviation is artificial intelligence. So artificial means it's not natural, it's not biological, but it's somehow hosted by something else, typically by a computer system. And a computer system usually has two elements, data or information, and something that does something with the data. So something like reasoning or communication or something like that. And what I will talk about a lot in this lecture is these two elements. What you do with it is called the task, and what it is about is the domain. So what I would like to tell you today is that it's very difficult to talk about AI in general, but you always have to talk about specific applications with a specific task and a specific domain. Okay, so let's do some examples. Now, if you don't do artificial intelligence, but you do artificial flight, you get this picture here. So inspired by birds, you can study how birds stay afloat because the way that the air flows over the wings, the physics of flight is the same for both airplanes and for birds. The physics behind it is the same. However, they do it in a different way. Birds, they actually move, and airplanes have a jet. So they use the same physics in different ways. So that means that artificial flight is different from natural flight. In the same way, artificial intelligence, it's based on the same principles of what is intelligent, for example, the mathematics behind it. But it may turn out to be quite different from the way we as humans do it, or also how animals do it. And what is also important to remember is that what we find easy is actually quite hard, and what systems find easy, what is easy to automate, things like chess, are actually relatively easy to do, because chess is a formal game, it has rules, and therefore it can be automated much more easily. Okay, so let's talk about intelligence without systems. So what is intelligence in general? So if you think about you or your friends, or maybe your sister, and you call them stupid, so not intelligent. So under what circumstances do we talk about intelligence? Well, sometimes we talk about the CIA, an intelligence agent, but that is not what we mean here. Sometimes we say that somebody's intelligent when they know a lot, when they're smart or clever in a sense, right? So they can do things, in particular, they can think much better than other people can. For example, they're good at mathematics in school. If somebody knows a lot of mathematics, we say they are smart. And all of these cases also apply to machines to a certain extent. Now, if you think a little bit more, what is really clever is that that you don't do things twice. So if you make a mistake, that you don't repeat your mistake. And in a sense, that's about learning. So you improve over time, and you make it more and more efficient or more clever. So this is the type of intelligence that we want to talk about today, and it's the type of intelligence that has been automated in artificial intelligence. Okay, so what you typically know about AI, I don't know much about you, but many people for the first time hear about artificial intelligence from films or from books, from science fiction typically. And now, by the way, more and more of the functionalities that you see in these films, like here, for example, the Star Wars film with R2-D2 and 3 CPU, more and more of these capabilities become now available too. For example, ChatGPT is able to sustain a kind of a dialogue, just like these robots did. They can use speech to a certain extent. They can also recognize the speech of humans. So let's do a list. Can robots or can AI systems play chess? Well, yes, they can do this actually much better than humans can. So already in the 1990s, there was a chess system by IBM, Deep Blue, that beat the world champion at the time. Can they play football? Well, kind of, but it's actually very hard to get the physics of kicking a ball right. It's very difficult to make a robot win or score a team. And what is also difficult in football is that you play together. You have to be aware of where the other players are in the field. So being part of a team is actually something that is very difficult to automate. Can robots or AI systems write sonnets, poems in the style of Shakespeare? Yes, they can do this. So ChatGPT and GPT-4 are examples of systems that generate poetry, and you can also adjust the style. So it turns out they're quite good at things that are related to text by now. And this is a recent breakthrough. Can they tell jokes? Yeah, kind of, but they're not really funny jokes. So there is something about humor that is difficult. So they can produce things that look like jokes or like the types of jokes that a 10-year-old kid would like, but really adult jokes that have some sort of attention and also social meaning in a group, that's much harder. Can AI systems do all of these things at once? As you have seen in the film, these robots can do a lot of different things. And then the answer is definitely no. So far, AI systems can do only one thing at the same time. They can do only one task, and they are always applied in one individual domain. For example, in healthcare, or in transport, or in the financial domain, in a bank. So a system that is designed to work in a bank cannot also work in healthcare. It's a different system. And this will also take away some of the misunderstanding that people have about AI taking over the world, for example. Current systems cannot do more than one thing at the same time. Okay, so now we continue on this line with a small historical timeline. And there are a lot of words here that you are not expected to know yet. So maybe by the end of this course, this series of lectures, you will know more about these things. What is important to see here is that AI is relatively old. It's a subfield of computer science, and it started already in the 1960s and then was developed further on. Huge breakthroughs in the 1990s and 1980s around expert systems. And then more recently, deep learning and ChatGPT, generative AI is now the new breakthrough. Also data science, the availability of big data and how to analyze that, becoming more and more mainstream and being applied in practice, in businesses in particular, is a recent trend. But yeah, much older is already a lot of theory and a lot of thinking about AI that makes it a science. So for example, in the 1980s, a scientist called Newell developed the knowledge level hypothesis, showing that any interesting problem that has to do with knowledge can be reformulated as a form of search. So just like you can search a path through a space, if you are planning your traveling, you can translate any interesting problem into a kind of a space, and then you can search for a solution just like you would search for a path, a travel. And this is a very fundamental trick to model different domains and different problems. What you can also see here in the color coding in blue and in red is that there are different types of systems, and roughly there are 2 families, and often they are combined. However, it's important to realize that it's not only the most recent machine learning applications where you find patterns of behavior in data. Sorry, there should be an S here, discover patterns in data. But also much older systems based on the mathematics, essentially rule-based systems. So suppose that you know the rule that if A, then B, and you find out that A is the case, then you can conclude that B is the case. So this simple logic based on Aristotle's logic has been used a lot in AI systems, and in particular in the 1980s and 90s, this was the most dominant way of thinking about AI. Okay, so what you learn from this timeline is that there are many different developments, and that actually AI as a field of research is very diverse. You can see many different types of applications and different theories being applied. Okay, so now I'm going to give you some examples of applications, and these are all taken from the Moodle, from the book that you're using. Application number 1, self-driving cars. So a self-driving car is a very clever machine, and it can do many different things in order to be successful. For example, it can watch the road by means of a camera and understand what's going on. It can control the speed of the car, just like a driver would use the gas pedal. The robot or the autonomous car can control the speed. It can also brake. And more importantly, if you brake while you're in a turn, you also have to brake in a different way. So all of these things are related. So if you're braking, then your vision should also give you feedback on the change of vision in the road. These are all sort of short-term tasks, but there's also a long-term task. If you want to get from A to B, you have to do navigation, just like a car navigation system does. And a self-driving car integrates all these different tasks together. What is the domain? Urban traffic. Now, what is interesting about this domain is that it's actually a very difficult domain for automated systems to handle. So one thing is that traffic is not on your own, unless, of course, you live in Australia in the desert. There are other people in traffic. And if you want to be safe, you have to understand and predict what the other traffic participants are doing. And you can also see, so a lot of these tasks are done with machine learning applications, with data, in this case, from the sensors, from the camera and from the distance sensor to the car in front, and from that the machine can learn. So here you can see an example of how that looks like. So you can see a blue car coming from the right, and that is being recognized as a car and also as something that will obstruct our own car. So it means that our own car now has to brake. Why? Because this car is coming from the right-hand side. And we know by the rules of the road that cars coming from the right-hand side have priority. So you can see that you both need machine learning techniques, understanding the camera image, and also you have to have some sort of an understanding of rule-based systems, because this is a strict rule that also has to be applied in this autonomous car. Okay, so I hope this example is clear. Yeah. And I can see in the chat that people are reacting to what I said before. Yeah, we can do all of this later. Okay, I'll continue with the second example, content recommendation. So this is very common, I think, for all of us. If you use an online bookseller like Amazon or different ones in different countries, it will recommend to you books based on what it knows about you. This is actually my list from this morning. And you can see that there are some books here about philosophy. This is by David Lewis, very famous book. Then I like novels about Napoleonic wars and sailing ships here. by Patrick O'Brien. So it just looks for the author of what I bought in the past, and then it tries to find similar novels to what I've bought in the past. And here is some more textbooks for my work. This is about epistemology. It's another field of philosophy. So you can see there are different clusters here. So there is a cluster of these books, and there is a cluster of philosophy with this one and this one. And then there is an odd one about history, and this is again philosophy. So it's trying to group all these books into categories, and then based on that, predict what I will buy next. Now, what is interesting here is, so this is how it works. It collects a user profile of me, how I behaved in the past. So basically my name and address and the language I use. Also my payment information, but also the books I've bought and the books I've searched. And every book has a title, an author, and a genre, and the year, and the price. So all of this is called data. Lots of data about books. And then it tries to look for books that are similar. So here we can see a group of books, for example, about philosophy. And here we can see a group of books about, for example, action and sailing. And this is a strange book. It doesn't really fit, right? It's an outlier. And now it tries to predict what I will buy next. So probably I buy some other book in the same group, and that's a new one. So it shouldn't recommend old books. So I hope you understand that the logic here is based on books that are similar. And it does this by somehow measuring what we call the distance between various books. So if you map a book in a space like this, there is a genre here, the different types, action and philosophy and so on. And here are the words in the title, so in the sense that describes the topic. And here is the author. Then you can group books that are similar, that are closer together. So that's a distance measure. Now, once we have that, then it can also learn from other people. So you know that Amazon sometimes says something like, others who liked this book also liked another book that is similar to that. So based on that, it can predict books that are new for me, but other people have a similar taste. So this is the application that you're all familiar with, and I hope you understand a little bit now how it works. More about this will be explained in the lectures on machine learning. Oh, there's a very detailed question about the specificity of the task. If you develop a system dedicated to management, selection of the proper dedicated system, yeah, the issue is solved. Well, management is actually like driving a car. It's a collection of different tasks. So think about what management does in a company. They do many different types of things. So for example, they have to predict what will happen in the future, and then they have to take decisions for now. For example, who should do what? Shall we cut costs or shall we invest? They should also motivate people to work. They should do an assignment of tasks. So please realize that the word management in everyday words collects many different tasks. And for each of these tasks, you can build a different system to help the manager. Does that understand? Is that a good answer to your question?
They have not responded.
Joris,
Yes.
I
Okay.
think
Yeah.
it's preference that you go through the talk, then you answer the question after your presentation. It's
Yeah,
better.
but this was really about what I said before. So
Okay.
Oh,
okay. Yeah, I'll get to the how to preserve people later. That's a very good question. Thanks. I'll keep you posted. Okay, so let's continue with the third example. This is again from the Moodle, from the chapter. All kinds of examples of image and video processing. And again, my point is here that you can do this with different tasks and that it makes a lot of difference. So suppose we do face recognition or fingerprint recognition. So your fingerprint is unique for a person. The pattern of the lines is uniquely identifying a person, and therefore you can use a fingerprint to identify people, for example, in case of a crime. Now, suppose that we have two different tasks. One is search and the other one is check. So in search, it means I have an image taken from a suspected criminal, for example, and I'm trying to find if we have seen this same image before in a database of fingerprints. In the second case, I already have some suspects from the crime scene. So I know in advance the fingerprint of those people, maybe 5 people who have been present. And then I'm trying to match this particular fingerprint, the suspect I have in front of me, with the 5 cases that I found in the crime scene. Now, the second one, the check case, is much easier. I hope you understand that this is a different task and it's easier, and you can also do it with much higher confidence. So you are much more certain that you have a real match. Now, what happens sometimes in the past in the Netherlands, there was a political scandal that a system used by the police for the second case for checking was reused in a different way for searching. However, it was never built for that purpose, and therefore it produced very bad results. People were convicted without a proper reason, and later people showed that the statistics behind this was actually wrong. So the confidence that the system gave was never accurately calculated. So if you get the task wrong, you can make really big harm. In this case, the municipality that used this system was taken to court and it was acquitted. Okay, so how do these systems work? You have a kind of an image in the computer, and then that image is translated into something called a feature. So they are indicated here with these little circles, and these features together, they are like a profile, and then you can search for similar images, just like in the case before, in the database with other fingerprints. And if your confidence level, based on this distance measure that I talked about before, is larger than some threshold, then you say it is a match. If it's lower, then we say there is no match. Okay, so that's the third example, image recognition, specifically for fingerprints, but you can also have a similar story for face. Okay, so now, how can we define AI? Well, what we've seen is that AI is a sort of a group of many different types of things that are cool. And there's sort of every time that a computer can do it, then we say it's no longer AI, because then it's sort of boring. So that doesn't really work, that definition. A much better definition is to look at the characteristic properties of AI applications. And the critical ones, also from the book, are autonomy. So the system can do this independently of a human guiding it. And adaptivity, it has to do with learning or improving performance. Okay, there is also an exercise, and I would very much like you to do this exercise. So after this slide, you are now in the position that you can do this exercise on the definition of AI. I would like to move on and talk about tasks and domains. So here you can see a picture of different types of tasks. This is based on a methodology from the 1990s, the Common Cuts methodology. And they're all about knowledge, all about sort of interesting, difficult tasks. And you can see 2 families. One is analytic, so for understanding something, and the other one is synthetic, for making something, creating something. Classification is the most commonly used AI task in machine learning. So you have some profile, and on the basis of the profile, you classify some object, for example, a book, of being of a certain class. Is this book belonging to action, or is this belonging to philosophy? In what type of genre does it fit? So classification is a very common task, but there are many other tasks related to that. So what a doctor is doing is called diagnosis, identifying what illness a patient has based on the data of the patient, the symptoms. If you do classification and you do it repeatedly over time, for example, in a factory, then it's called monitoring. So you see if something is changing, if the class that we're classifying is different from before. If you do it in an exam, it's assessment. So we classify a student as either passing the test or not passing the test. And if we're trying to look at the future, we're classifying now not the past data, but we're trying to predict what will happen, then it's called prediction. And so all of these are different variants of analytic tasks. In a similar way, there are synthetic tasks like design. So designing is making, and an easier version of that is configuration. So if you think about the way that a modern computer is constructed, you start from the processor and then you add the memory chip and so on, and you assemble it together in such a way that all these components fit together. That's called configuration. And that assumes that we already have components that fit together. Design is much harder because you also have to design how they fit together, just like Lego blocks. You have to design how far apart these blocks are. In a similar way, also planning is a synthetic task, modeling, assignments, and scheduling. Okay, so we've seen different types of tasks. Now I want to zoom in on classification because this is the most common one. And what you can remember is that it's always a relationship between two things: data, the factual space, and hypothesis, sort of the understanding we have of the data. So this is a stupid example, but you can hopefully see that this is the same type of reasoning that a doctor is doing. Suppose that I have the following symptoms. I have a fever. I'm a bit dizzy, nausea. I don't know. Yeah, I'm unsure, and I'm coughing. So, what type of illnesses can explain this behavior? Well, there are several possible hypotheses about what illnesses I could have. For example, it could be a common cold. It could be very bad, pneumonia in my lungs, or it could be food poisoning. So based on these different choices, I now have to ask the patient for further information to identify which of these things can be ruled out. So by learning more facts, for example, if there would be a high fever, then it's likely to be pneumonia. However, there is no high fever, so pneumonia is out. Also, you could ask, did you vomit? If I vomit a lot, then it's likely that I have food poisoning. But if I don't vomit, then food poisoning is out. And so by learning more facts on the left-hand side, the number of possible hypotheses on the right-hand side becomes less. So these are all the things that could still be true given what we know. And here is what we know. And this is like a dialogue. You go back and forward between the facts and the hypothesis. And you do that based on general knowledge, in this case, that links diseases to symptoms. And so this is a typical way that a knowledge-based system would work. I hope this is clear. Yeah, there is a question about classification. So classification is one of the most general tasks, and it reappears in a lot of applications of machine learning. So it's very abstract in a sense. So this diagram, this one here, shows many different tasks, and classification is one type of task. So I hope that answers that question. Okay, now let's continue a bit more. So once we have different tasks and we have different domains, we can combine them in different ways. So suppose we have a doctor, like here. This is the doctor asking the patient. The doctor is doing diagnosis, trying to find out what the patient has. So the domain is human medicine. Now think about a car mechanic. So my car is broken and I go to the garage. Now the car mechanic is also doing diagnosis, trying to find out what's wrong with the car. However, the domain is different. Now it's automotive. I can also keep the domain the same and switch to a different task, right? So if I have a database with a lot of knowledge of how an engine is constructed in a car and brakes and all these things, steering, I can use that also for designing a new car. It's a different task, but it's the same, domain. So the point here is that you can reuse these models for different purposes. Either you use the model that you have for the task, for the reasoning, or you reuse the model that you have for the domain. So what we learned here is that we have different models that are part of an AI system. Now, what different models there are, this is another model, this is another overview from the Common Cuts approach. For any interesting AI application, you will need a task model, like we've talked about. You will need a knowledge model, like we've talked about, but also a model for communication about this. So, you know, for example, a doctor uses a lot of medical terms. Sometimes they're in Latin. And that's a different way of communication than if you talk to your friends in school, for example. There also needs to be an organizational model. So a doctor is only allowed to prescribe medicine. A nurse cannot prescribe medicine. That's not allowed in the organization, right? So who is allowed to do what is part of the organizational model. Similarly, an agent model, if we would have a computer system that replaces part of the reasoning here, that also needs to be modeled what that one is doing and how that interacts with the doctor. So typically a computer system will not replace the doctor, but work together, for example, in interpreting images in order to do the diagnosis. Okay, so what we learned from this slide here is that there, in any interesting AI system, there are many different models, and you need a combination of these to get it to work. This is not just a hypothesis. This is actually being done. So this is an example. This is maybe for you at home. If you want to, you can look at these videos. This is research being done in Utrecht University. I learned about this in a conference last year. Suppose you have a doctor and a patient discussing the illness, and there is a computer system built into the ceiling of the office of the doctor with a microphone. It hears what is being said, and it understands the medical terms, and then it summarizes the conversation and puts it into an official record, a medical record. So that saves the time of the doctor. Now, the doctor doesn't have to type in the results, but the computer is in the background and doing this for the doctor to save time. And that means that a lot of different, again, tasks need to be done. For example, whenever a medical term is used, they have to be recognized to be special, and they have to be linked to knowledge bases and checked if that fits to the illness that the system thinks the patient has. And so parallel to the doctor. Also, when the treatment is discussed, the system could already make a treatment plan and add this to the files, to the record. And similarly for medicine, already you can make a prescription and send it after it has been verified by the doctor, send it to the pharmacy. So this type of system will increase the efficiency of healthcare. And allow the doctor to spend valuable time with the patient rather than spending it on administration. Okay, so this is again from the Moodle. We talked about AI as a sort of an umbrella term, a general term, and it fits many different shapes and sizes. So things that are related to AI are machine learning, deep learning, data science, and robotics. And here are some descriptions. Machine learning is sort of a general type of systems that improve performance in a given task by more and more experience. So that's true for something called reinforcement learning, or else from data. So the idea is, again, find patterns in data. Reinforcement learning, suppose that you have a Facebook channel and you give a thumbs up or you give a thumbs down. You, in a sense, you reward somebody's post, and these pluses or minuses can be used as feedback. So that's the type of learning that is called reinforcement learning, the learning where you use feedback. In all other cases, you need a data set beforehand. My colleagues will talk a lot more about machine learning in the later lectures in this course. a special type of machine learning that is nowadays very prominent is deep learning. It's a type of learning architecture that is based on neural networks. So just like in biology, neurons in our brain, but only the mathematical structure of that. And why it's called deep is that it has several layers, and some of these layers are hidden, so they're not immediately inspectable for a human user. So earlier we talked about features, but in this case, the features can no longer be understood by a human. So suppose that you have a deep learning system that can classify a disease very quickly. However, it is not transparent why it classified that disease. And so it's not clear. There's no rule or something in the data. It's very accurate, but it is not clear what features cause this to be. And this difficulty, this transparency lack, leads to a different field of research, and that will be explained by my colleague Amro Najjar in a special lecture on real-world AI systems. Okay, other related fields are data science. So this is sort of a big umbrella term for all the stuff that is done with big data and analytics, and it often uses ML techniques, machine learning techniques. And then robotics, like we talked about, this is artificial intelligence systems, but then put into a physical thing in the real world. A robot is a human-like moving thing that can, for example, talk or hear or walk or move. Can also be used in for example, car factories to make cars and so on. And robotics is the whole field of study where they try out how to do this in the best way. Okay, now we talked about many examples of AI applications, but you can also talk about AI as a sort of a phenomenon in itself, and whether we actually want this. Is this a good idea? It's a bit scary, perhaps, that machines or that computer systems are intelligent. And you can also talk about the question in general, when is something intelligent? And suppose I meet an intelligent system, how do I find out that it is intelligent? So this is the question that was asked a long time ago by Alan Turing in the 1950s. And he proposed something called the imitation game to find out how do we know that a system is intelligent. And the idea was, well, suppose there is some interrogator and it tries to distinguish between a human and a simulated human, a computer system, and it cannot determine which of these players is the computer and which is the human. Well, if it cannot distinguish, then the computer has passed the test. And in fact, for some tasks, it has already done that. So we talked about chess already and some things that have to do with text, generating text. Okay, now suppose that we do it like this and we have this Turing test. You can still ask, like in philosophy, people like to ask questions. So is simulated intelligence really the same as intelligence? Well, for chess, if you simulate chess, that's actually the same as chess, right? It doesn't matter if you play chess on a wooden board or on a computer screen or just on scraps of paper. The essence of chess is that it's an abstract game. So if you simulate chess, it's still chess. So if intelligence is like chess, then there is no difference between simulated intelligence and real intelligence. But if intelligence is like, I don't know, telling jokes in a group of friends, it does really matter. A simulated joke is not a real joke because it's not funny. So this is where the philosophy becomes difficult. And it depends to what part of philosophy you belong, how you answer this question. So some people believe that intelligence in general is like chess. It's an abstract thing. And if you simulate it, it's the real thing. And other people say, no, it's really important that it's different. And a related question that people ask is, does it matter what type of thing is hosting this intelligent behavior? Does it matter that it is a biological being, a human, or an animal, perhaps, or a group of humans? Or is that not important at all? And so can a computer also display intelligent behavior by definition? And I think here most people are more liberal, and they would say yes, a computer can also display intelligent behavior, and you just have to find out if it's good enough. Here it also makes sense to make some distinctions, and again these are taken from the book, so you can check them later. A difference between general AI and narrow AI. Like I talked about, general AI is for any intellectual task, and currently that's impossible. Although ChatGPT can do many tasks, it can still not do any task. So it can only do tasks that are related to text and to language. And even that only limited to, for example, English and other languages. So definitely not all. And most AI is narrow AI. It's for one task and one domain only. Another interesting distinction is between what you want to do with your AI. So originally, when people started with AI, it was part of cognitive science and part of a movement in psychology to help understand how humans do this. So by analyzing something in the abstract, in the mathematics, you also understand a lot about it. For example, what is intelligence in general? By trying to simulate it or to automate it, you learn a lot about it. For example, in natural language understanding, a lot was learned about grammar. That is also true for human languages. Or in vision, in your eyes, it turned out that if you build a computer system to do vision, you get exactly the same layers as humans use in their eye system. However, that's rare, and more common is weak AI, where it's just seen as a type of engineering. So it doesn't matter if you have a deeper purpose. What is really important is that you improve efficiency or effectiveness of a task in the domain. And this is, I think, the more common idea nowadays. And so AI is just a collection of tools and techniques that can be used in a clever way. Okay, so now we're almost there. I did want to talk about the dark side of AI, and I also had a question about this. Can AI systems do harm? Well, yes, very clearly, because many of the weapons that are now being used, for example, in Ukraine, are AI-based. They have guidance systems that target bombs. So yes, they do harm. And it's also interesting to analyze for these autonomous weapons how they are controlled. So it's important that these AI systems are not independent completely, but that there is a form of human control over who determines the target and who is responsible for that. Is it possible that AI systems rebel against a human owner, do something that is against the will of the human? Yes, in principle, that's possible. However, this is not the way these systems are being built currently. Can AI systems take over the world? And there the answer is a categorical no. Maybe the closest I come to that kind of conspiracy theory is that AI systems would take up so much electricity that we can no longer heat ourselves and switch on the microwave and so on. And so in that sense, in an economic sense, it can take over the economy, but not directly, and definitely without. It's impossible for systems to go beyond the borderline of what it was designed for. Do robots or AI systems have a moral sense? Well, that depends a little bit with what you mean by that. They can, for example, distinguish right from wrong in the same sense that they can do machine learning. They can find patterns in data, and they can certainly classify behavior as being right or wrong. But does it really understand that behavior? And so in a moral sense, I think the answer is no. So it can simulate these decisions, but it doesn't really care. It's still a computer system, and yeah, they don't have the capacity to care about the outcome. Can we trust an AI system? Well, yes, in a sense that it is reliable, predictable. It does as we expect to. Can AI systems trust us? That's an interesting question. And unfortunately, I don't have much time to go into that. So this example will come up later. I will do this one also. This is a small example of a robot that says no. In a sense, it rebels. This is based on our own research recently. Suppose we have a computer system that gives a recommendation for a recipe for food, and the user asks for a hamburger, and then the system says, no, you can't have a hamburger. And then the user asks, why not? And then the system will explain, well, you said you want to lose weight. To achieve your goal, you should eat no more than 220 calories per day. And a hamburger has 294 calories. So no. So here the computer sort of rebels against the human. It says no, but it is in the long-term interest of the user itself, because earlier that user indicated that they want to lose weight. Again, this is an example of a specific task here, recommendation with additional explanation, and the domain is food and health. And this is the example that you will have to look up yourself. So later, if you get the slides, you can click on the link and you can see this move. And the point here is that this robot is going to walk forward when the human here asks it, and then it will refuse to do that because it doesn't want to fall off the table. And then the human will say, I can catch you. And then apparently the robot trusts the user in a sort of simulated sense. So this little video, this is from 2015, makes you think about how a robot relates to a human, and also that we should care about the robot, for example, to preserve it in line with Asimov's laws to protect the existence of the robot itself. So even robots have rights, perhaps. Okay, so to summarize, there are limited circumstances where AI systems can rebel and say no. However, they always relate to the long-term interest of the human who developed it or who installed it. Conclusions. It's hard to define what AI is, but we can characterize some properties, in particular autonomy, that it takes decisions without direct human control, and adaptivity. It learns and adjusts to its environment based on data. And second, an AI system cannot do many different things. However, it is always built for one specific task and domain. There has been enormous progress lately with ChatGPT for text, but AI systems cannot do all tasks and all domains at the same time. And in particular, they're not very good in things like context dependency, uncertainty, incomplete information, or filtering out factual errors. And I hope you will get many more examples of these in the upcoming other lectures, which are listed here. Thank you for your attention, and I'm looking forward to hear your questions and to answer them.
Thank you, Joris, for the nice and amazing presentation. And thank you, dear participant, for your question. Yes, so we have.
Oh, there's a lot.
Yes, I collected them in documents, so I will start with the first one. Hope that we have enough time to answer all of them. So, okay, I will start by the first one. Football is hard for AI because of the motion involved or because of many players in the team? What do you think?
Both, yeah. So both of these things are different reasons that make it hard. So in the around 2000, people developed something called the RoboCop, where they got robots to play together in a team. And there was also a simulation game, so simulated robots, which don't have the difficulty of actually kicking the ball. and that was more focusing on how you play together in a team. For example, with the defender and the striker, and recognizing that if somebody is playing a certain tactic, that the other one should support the other one in that tactic. Typically what happens in this research field is that you separate the difficulties and you treat them one by one. So playing together in a team is a different problem from kicking the ball physically and estimating how hard you have to kick.
Yeah, that's true. The second question, AI will cover medical service in a nearly future, doctor. As example, as you have got involved in many researcher, is there a kind of machine medical service to be implemented or replacing medical service?
Okay, I do not believe at all in replacing people. What happens is that increasingly humans and computers are seen as a team. So think, for example, about what the doctor is doing when they interpret your radio image. So you get
Scanner, yes.
a scanner, exactly, a scanner image. Now, this type of recognition task is much better done by machine learning and by AI. So the specialist in the hospital who used to do the recognition of these photographs, they are being replaced, but the doctor still remains and now uses these intelligent systems to help with analyzing the scans. But they make a decision what type of treatment you need, to check also if you follow the treatment, if you can learn anything from other patients and so on. So why this is difficult to replace the doctor is because the doctor does so many different things, so many different tasks, and you cannot replace all of them.
Yeah.
Step by step.
Yeah, I totally agree. The third question is about autonomous car. How AI resolves situation where to preserve a person, he has to disrespect road rule. How that kind of situation are learned by artificial intelligence, by AI?
Yeah, that's a very good question. I was hoping actually when I showed this picture here to talk a bit about that moral sense, right? Because that's also an example of what you mean by that. So you have a strict rule of the road about priority, for example, and you have another rule that you should always be a careful driver, or that you should preserve other traffic users. And that rule is like the first rule that is more important than the normal rules of the road. So that means that a computer system that implements that would be basically steering, and that would be autonomous. Currently, systems are almost getting there, but they're not good enough to be allowed on the road by the official traffic authority. Only in limited cases, like in Australia in the desert. And the reason is that this moral sense is one of the problems. The other problem is that it's difficult for humans to give responsibility to a car. So suppose that the car would hit somebody, who is responsible? Is that the manufacturer of the car? Suppose it's a Volkswagen, would you sue Volkswagen that they created the car that killed somebody? Or would you say, well, this is part of normal traffic? And that issue has not been solved in society. So that's actually a non-technical problem that society has to solve before it allows cars on the road.
Yeah.
Thank you. There were other questions before that, Sana. There was one about medical services by Rafael Vitor Mendes. He or she asks, I will cover medical services in nearly future. As example, as you've got involved in many researchers, is there a kind of machine medical services to be implemented or replacing medical services? So I think the person meant, would AI be able to replace certain fields of medical services in the future? What do you think?
Yeah,
or even a doctor?
I think we talked a little bit about that when Sana related this question. So yes, some fields of medical services, and so not related to what the doctor does, but for example, what this radiologist is doing in interpreting the images can be replaced because that is much better done by the computer. What is very difficult to replace is the overview of remaining in control of the treatment. What you can also see, in particular in hospitals, is that they organize the hospital much better and that you streamline the workflow, as you call, so how nurses and doctors and administrative people work together. And their automation computer systems also are very, very helpful. And that speeds up also for the patient. So if you go to the hospital, you get many appointments one after the other, and therefore you don't spend so long time in the hospital. And also for the hospital itself, it's much more efficient. And their AI is often used in analyzing the patterns of how patients go through the hospital and then redesigning the workflow to use that knowledge and to make it more efficient. So I think that's related to services.
Yes, that's good. And there was a second question before that on information systems. Can AI be used in assisting, or are there any examples in assisting change management when implementing a new information system? So change management here.
Yeah, this is a specific topic. So I know, I happen to know about this. I can answer your question, but for the other people, don't worry if you don't know. So change management is what happens if you change the way you work in an organization. So for example, in the software industry, if you start to work agile by Scrum or something. So people who in the past, they knew what they were doing, and in the future, they have to change what they are doing. I don't think that there are AI systems that can help in the transition itself in the management, because this is involved, like I said in the last slide, it involves a lot of uncertainty and context, and that is hard to automate. But on the other hand, if you implement an AI system, for example, in a hospital, it will often involve a lot of change management, because people will have new responsibilities and new tasks, and other tasks will disappear. So the example that I gave earlier about the radiologist doing the interpretation of the scan, that task will disappear. So the radiologist will have to get a different job. And that's part of change management. And that's often not easy. That will lead to friction and to people complaining and so on.
Thank you for the response. Sana, we can't hear you. No, we can't hear you. No, maybe I should continue. I also have.
I can see, yeah. Can I say something? Earlier,
Yes.
I noticed a question from Claude that the presentation did not advance.
Yes, this was fixed.
Okay.
The person logged in through a different browser.
Okay. Thanks. Yeah, because that's quite critical, right? Otherwise, I would have talked in a void.
No, this was fixed. And there was a follow-up question to a response that you already gave. You responded to tasks taxonomy, and the person asked, is there a general classification or only a classification available for AI stuffs? So it was this question. And then the person followed up with the question, clarification on the question. My question was more about, can I also use the task tree to type my own tasks, or this tree is only for AI type of tasks?
No, a very good question. Yeah, no, this is a nice example of strong AI. So I think this is a general, this one, no, sorry, one further back, this one. So this would work also for human knowledge intensive tasks. So the designers of this methodology used cognitive psychology, so about humans, to find these tasks. So it's supposed to be a complete list of knowledge intensive tasks for humans. as well as for computer systems.
And that might be shared with your presentation if you allow.
Yeah, of course. Yeah, I can also, I will later remove some spelling errors, and I will add a link to this Common Cuts.
Okay, perfect. That would be nice. Then there was another question: is between on the difference between diagnosis and classification.
Yeah.
Is diagnosis not classification according to your
Yeah,
opinion?
very good question. I like this because that shows that you understood. Diagnosis is a special case of classification, namely one where you identify what is wrong. So you classify a case where something is wrong because of some root cause, some underlying problem or an illness. And moreover, for humans, it's the case that diagnosis is always combined with a treatment. So when are you ready with your diagnosis? If you know enough to prescribe a treatment, for example, a medicine. Similarly, for the car mechanic, when is the car mechanic ready with the diagnosis? When he knows which component to replace. And it doesn't really matter why that component was broke, because what you want is a working car. So diagnosis is always classification enough so that you then can take action to fix it. Yeah, and you can also see that monitoring, for example, is a special case of classification, namely one that is repeated over time. And so all of these other ones here are very much related to classification. That's also why it's so common. Another
Thank you for your
question from the
response.
chat. AI,
Yes.
for example, ChatGPT is very good as the. Yeah, this is a very good point. So yeah, and thanks for mentioning this, because this was on the agenda for today. I was supposed to talk about the importance of data. And so no AI system is more clever than the data that you feed it. And also the other way around, if you feed an AI system bad data, for example, data with bias, gender bias, that it thinks that men are more important than women, then it will also repeat that. And that also explains why we are certainly not there yet, and that we have to be careful about the moral side of AI. So in particular, I believe that AI should always be embedded in a shell of humans and engineers who make sure that it stays within the boundaries for which it was designed. So that's related to this.
There's another good question.
Can you hear me now?
Yeah. Yes, we can hear you.
Yes, I don't know what happened to my browser. I lost you for a few minutes.
Okay, come in,
I wanted-
Sana. Tell me.
Yeah.
Did you want to relay another question, or?
I don't know the question that you just answered. Yeah, because I have a list, but I don't know what I missed.
Maybe the one from
Okay, did you
on
ask
statistics.
did you answer the question about the limitation of ethical constraint or not
No.
yet? Okay, so the question is, what is the limitation of ethical constraint in AI considering decision making that may harm or help physical person?
This is difficult to answer because I don't really understand the question.
What is
but
the
it's also
limitation?
because I'm trained as a computer scientist, maybe that's why I can't understand.
Maybe
right?
I can.
It's a good question, but
Yeah, I think I understand the question. I can answer it if you want.
Please.
So yeah, the major limitation is when we target the ethical constraint in AI is the difficulty in programming complex ethical consideration into algorithm.
That's
because
yeah.
Yes, that's the limitation, I guess.
Okay, I can explain a little bit
yes.
how my colleagues do it, because actually this is something that some of my direct colleagues are working on ethical AI. Sometimes this is called machine ethics.
Okay.
So how do you program moral or ethical decision making? And again, there are two approaches. One is the rule-based one, and the other one is learning. So for the rule-based one, it's just like in law, you look at the law books, and you try to go, if this is the case, then you do that. If this is the case, then you do that. And the problem with these rules is that it's very difficult to make the rules context dependent. And so these rules always are limited by, in some cases you do it like this, and in other cases you do it like that. And the rule set is difficult to distinguish. So the limitation for rule-based systems is that it cannot very well distinguish different contexts.
Yeah.
And so if you think about what is allowed on the internet, if you're chatting, what is allowed in a work environment or on LinkedIn is completely different from what is allowed if you have a chat with your teammates from your sports club, where you make sort of dirty jokes, and that's perfectly fine within that group. But if that dirty jokes reappears in your work environment, then you may be sacked because it's inappropriate. So that context dependency is very difficult for rule-based systems. For machine learning, the limitation is that it cannot distinguish between what is morally right and wrong and what is just an exception. So in the data, you cannot see if something is just very rare or if it's not allowed.
Yeah, because the AI system may not fully comprehend or understand nuanced human value and the context of certain decision or situation, which lead to
Yeah, that is
unintended
very true.
consequence.
Yeah, what it can do is simulate human value. So it displays behavior which is similar to what humans do when they value judgment and ethical decision making. And in that sense, it can also be used for advising people who take difficult decisions, for example, in government. So in the COVID period, for example, systems were used to very quickly decide if somebody would be allowed in the hospital or would have to wait. So this is a very difficult ethical decision, but because it had to be done under time pressure, they automated this decision.
Yeah, and also I think it comes
But then it
from
was always done under responsibility of the head of the hospital. There is a human
yes,
still responsible, and they rely on the advice of the system.
yes,
So that's an important distinction.
yeah,
Yeah, very good question. Thank you.
yeah. Also, I think it comes from bias in the training data that can lead to make unfair and harmful decision. That's also
Yes. Yeah, very good.
another
Thank you.
limitation.
Yeah, so I hope people understand the word bias. So bias in the data set, that means that if you look for a lot of examples, then the examples are not fairly distributed. So if you look at texts over the last 50 years, then typically in most cases, the doctor will be a female. And if you say doctor, then you will, it will be a male. So later you will use the word he. So the doctor and he occur more often together than not.
Yeah.
However, this is something that you can learn from text, as the text was in the past, but it's no longer true for now, right? It's actually false because the doctor nowadays more women are trained as doctors.
Okay.
So this is an example of a bias in the data set.
Thank you. Thank you. I'm not sure if you answered the question about task taxonomy. Okay. So the question is
I
that
did,
a general
yes.
classification?
I think he did. Yeah.
Do you hear me?
Yes.
Yes.
We,
The question is about taxonomy. Is that a general classification or only classification available for AI stuff?
Sana, we responded to that question earlier.
Okay, good. Another question is diagnosis not classification?
Yeah, we talked about that.
We
Okay.
had this one.
Sorry.
No problem.
Yeah. In related fields, statistic was also often mentioned, but I couldn't find a definition about statistic in the context of AI. How is statistic different or similar to AI, and how can I differentiate them? Could you please elaborate?
This is a very good question. I'm really impressed by this audience. Thank you. So statistics is the tool or technique in applied mathematics that has been used for a long time before machine learning. And also statistics finds patterns in data, right? So this is a very good question. The way they do it is a little bit different. So statistics uses formulas, and what you could say is, for example, that you try to minimize the variance, or you try to explain the variance in the data by your formula, and you try to minimize the difference, the error. And then you can measure that, for example, by the statistical significance. So this is very much quantified. It's based on numbers. Machine learning also finds patterns in data, but it doesn't do this with a formula, but by other techniques, for example, by tree-like structures, or by neural nets, or by features. And these are typically qualitative, so they are about yes or no, or different types of things. They don't always have to. It's easier if you do it with numbers, but it's not necessary. And it's also much harder for machine learning to find something like significant, because the underlying mathematical theory is much less well understood. So in a sense, statistics and machine learning is a sort of a gray scale, and statistics is more old-fashioned and therefore also much better developed, and machine learning is a bit more Wild West. In practice, our students in Luxembourg, when they do data science, they use statistics techniques and machine learning techniques, interchangeably. They use both.
Okay, thank you. One more question. We still have many. We will try to answer them in the Reddit platform because we come at the end of this webinar. So one more question and we conclude this webinar. Could you provide the case number identifier of the NL case you mentioned, where a system designed to check fingerprint was used for a search task?
Yeah, I think this is another question to show that you know much more than I originally thought. So, can you repeat the technical term in the beginning of the question?
Yeah. Could you provide the case number or identifier of the NL case you mentioned, where a system designed to check fingerprint?
You
was
want to have
used
a
for a
reference
search task?
to the web. I need to look for this. I did this on memory. So just to go back to this case, remember that there was search versus match, right? So if you are doing a match, you have a specific fingerprint and another specific fingerprint, and you see if they can be matched, meaning that the features that summarize this picture are the same, or enough the same to say that they match. For search, you do this, but you do this for all the different cases in the database. So you go through one by one through all the database examples, and then you see if it would match. However, this takes a very long time. So algorithms that do searching typically use a much smaller feature space. They summarize the fingerprint, and therefore they lose detail. They are not so precise anymore. They work faster, but they lose precision. And that means that if you use a system that was originally designed for matching, for searching, it doesn't work.
Okay. Thank you, dear Joris, for the amazing talk, for your time. Thank you for the time you give it to answer the question. Thank you, dear participant. I hope that you enjoyed our today webinar. As a reminder of our next webinar, it will be about the creative problem solving with AI beyond the conventional by the Professor Christoph Schomer from the University of Luxembourg. So the webinar is again scheduled at the same time from 13, and we kindly ask you to read the next chapter, which is about AI problem solving before the session. And also we encourage you to put your question in the Reddit, the question about the first webinar and also the question about the second one. So we will try to answer them. Yeah. So for those who want to rewatch the recording of this webinar, you will find them in the link of the Reddit posted at the post of the webinar 1. So feel free to use it. We will try also to put the presentation of the speaker. Thank you that you allow us to share your presentation with the participants. So thank you so much, and see you next week.
Thank
Thank
you.
you for organizing, and all of the students, thanks for your attention. Bye-bye.
Thank you. Thank you. Bye.